Good morning. I'm going to go off on a seeming tangent today. Something to do with one of the essays and articles I was working on a couple of years ago. And the article was called Einstein Notation as Matrices, Part 6.php. And the section of the article was called A Spacetime, Probably Christoffel Symbol. And it says we could envision a sort of goo with each particle in it assigned a value of n. For instance, the 4.5th particle would be designated n equals 4.5. I'm going to change the variable here because what I want to do is associate the goo. I'm going to call the variable here phi. It's a curly phi variable. And so this is basically being the numbering is going to be the numbering variable. And the reason I'm using this as my numbering variable has to do with rapidity. So the phi equals 4.5. I'm going to say, okay, I'm the guy with rapidity 4.5. So this is not real. This is not. It's just an enumeration because my actual rapidity, any observer that says my rapidity is 4.5 is wrong. From his perspective, his rapidity is going to be 0. But you could conceivably number everybody according to that. And then even though they're technically just using that just refers to a reference, it would be refining it to each particle carries a clock label tau. And so you could ask any particle, who are you? And it would respond with its value of phi. And you could ask it, what time is it? And it would respond with its value of tau, the time on phi's clock. There is a particle at the very center of the distribution who sits stationary at the origin. And he's not really any more stationary than anybody else, but we're going to call him stationary, and we're going to say his description is phi equals 0. It is the origin particle who is the holder of the coordinate t comma x. So he's holding a big ruler that says t along this way, or no, says x along that way, and he's also has the time t equals 1, t equals 2. And so you can imagine that this ruler, he's got a big ruler, and that ruler has clocks on it. And that ruler is stationary in his hand. So all the rulers in the system are constructed so they are measuring distances from this origin particle, and they're stationary with respect to that observer that calls himself the phi equals 0 guy. So if you ask particle n equals 5, actually this is incorrect. If you ask particle phi equals 5, who, this should be say who, he'd say, I'm phi equals 5. And what time is it? He would say, well, I'd look at his clock and he'd say, my tau equals such and such. Ask when and where are you relative to particle O. You can look at the ruler that he is passing by and read from it the value of x and t. So he's reading x and t from that ruler with attached clocks, which is basically this is Euclidean. Euclidean x's, they're Euclidean matching the phi equals 0. These are the Euclidean coordinates for the guy who calls himself phi equals 0. And I think what I was doing here is I was changing that x to x equals x. Boy, I wrote this really badly. So he's going to report what he reads off of the ruler as x. The little x represents the little x just represents ruler reading. So that's what I'm doing there. The coordinate on the ruler. Ruler reading equals, and then the big X actually represents the number, I guess. I think that's what I was trying to do. He reports X and T, so to keep his position X distinct from the coordinate X. So this is the coordinate X. This is the position, capital X. So each particle and its corresponding clock can move about with one limitation. They have to stay in consecutive order. The higher numbered particles can't pass the lower numbered particles, and this is why I call it a goo instead of independent particles. So each particle and its corresponding clock can move about with one limitation. Oh, I already said that. But with that in mind, they can stretch and compress. They can transmit sound along the x-axis. They can flow out like galaxies exploding in a big bang. Whatever you want, as long as they maintain that kind of goo structure. With the nth particle, and I really want to say, maybe I could say phi equals n, because phi is the rapidity, and I don't know. Yeah, I could have that difference with the nth particle located as a distance x from the origin, x equals x. Then one Christoffel symbol we could generate for this goo in flat space is this. And I wrote it this way, but I want to change some of these variables around because it would make more sense. Namely, I think I want to change these little x's to phis. Phis representing the coordinate of consecutive guys in the distribution. So phi is the consecutive guys in the distribution. And I'm kind of switching definitions. I'd rather not have that as capital X, but I'd just call that little x, because x is the actual coordinate space. The x is the measurement on the ruler. Tau is the measurement of the actual guy. T is the measurement on that ruler. So this is kind of mixed. It's weird because what I've done is I've mixed things up. So rho refers to the ordering something like tau x, y, z. Nu here represents to the ordering t, phi sub x, phi sub y, phi sub z. And mu also represents t, comma, phi sub x, phi sub y, phi sub z. So they're mixed. This actually represents proper time for one of those particles and Euclidean space. The nu and mu represents coordinate time of those rulers and the enumerated space of the goo particles. So as a total, let's just look at this part first, and this will be del tau x y z going to the right over del t phi sub x phi sub y phi sub z going down. And so what that does is it basically has tau x, y, z going across the top to the right, and then on the bottom we'll have tau x, phi sub y, phi sub z. So I'm just going to ignore the y and z and just do the first two parts like I did up here, except it's going to just be del tau, del, well, we'll just do del tau and then del x, and then del tau, del x. That's going across, and then del t, del phi going down, del t, del phi sub x, del t, del phi sub x. And what does that represent? That represents a few quantities. Del tau del t represents the clock speed of a given particle in the distribution compared to the clock speed on the rulers held by the observer, the phi equals 0 observer. Del x del t here represents the velocity of the given object compared to the time on, yeah, it basically represents the velocity of the object from the perspective of the viewer in the middle, the phi equals 0 observer. Del tau del phi sub x, what's that represent? I called that clock slope, and that's going to be from my, if I'm the guy at, say, phi equals 5, then looking at phi equals 4.9 and phi equals 5.1, is there a difference in those clocks? And it's kind of odd because I think with each of these partial derivatives, we're going to be saying every other thing is not changing. So in particular, I'm saying t is not changing. Phi sub y and phi sub z are not changing. Yeah, so that's what, I think that's what these partial derivatives are. When I have at the bottom del t, del tau del t, what I'm saying is phi sub x, phi sub y, and phi sub z are constant. When I say del tau del phi sub x, I am saying t, phi sub y, and phi sub z are constant. So that's a kind of an important point to make about these partial derivatives, that when I actually put them in this order, I'm putting constraints on all of the other variables in that list. But that, since I put it this way, I am not saying x comma y comma z are held constant. I'm just saying phi sub x, phi sub y, and phi sub z are held constant. So that becomes interesting when I come down here, del tau del phi sub x, I am holding t constant in this. So if I'm looking at a Milne distribution, I'm not holding, because tau goes like this, t goes like this. So if I held tau constant, well, del tau del phi, obviously holding tau constant isn't going to have any effect at all. Del tau is going to be 1. But I'm holding t constant and comparing, like, okay, here's a rapidity here, here's a rapidity here. What is the difference in time from there to there? So yeah, that is the clock slope as you go across. And as you get closer and closer to the bottom here, I think that slope is going to be, well, del tau del phi sub x. If you're looking at, yeah, okay, the clock slope, because if you are looking over here, if phi is big, if phi is large, I would not say that this is necessarily approximately 0. Del tau del phi, because remember this, the tau here is the same as the tau here. That means this is quite a bit less than the tau here. So del tau, keeping that constant, is actually getting smaller. And then finally we got del x del phi sub x, and again, when I say del x del phi sub x, I'm using this list, so I'm holding t constant, phi sub y, and phi sub z constant. So the main thing is to think about what is different looking at x, and x is the ruler measure between consecutive values of phi, which I think would shrink. I just did this morning. You can see the labels. These are labels of phi sub x. Here, the phi sub x, 0.25, is very close to x, 0.25. But as you move over and get to higher and higher rapidities, here phi sub x is still 0.25 between those two vertical lines, but x is much, much smaller. Dx del x del phi sub x is a much, much smaller thing. And then here from 1.25 to 1.5, again, del x del phi sub x is much smaller than 1 here. It's always going to be less than 1 in this description. But as you get further over, and you see infinity there, it pretty much approaches 0. The change in x for a sizable change in phi sub x, here going from 1.5 to infinity, gives a finite change in x. So essentially, the derivative, that partial derivative, would be 0 in that case. There's a whole bunch of other quantities that come about when we do the second derivative and we apply the new variables here, which is here I've labeled them t, phi sub x, phi sub y, phi sub z. So that's interesting that we'll have del. Okay, and this goes down, so it's del del t, and then it's del phi sub x. And kind of doing an outer product of these, which means we'll have one on the top here and one on the bottom. And question is, do I get acceleration, dispersion, heterogeneity in by doing that? I'm not sure. I'm going to take a little break now. Thanks for watching.